So, what we I am telling that these are one of the most difficult part of statistical mechanics, which are usually not taught in courses, and probably some of you who are here know the difficulty, some are not there. So, I will slightly repeat about that. So, basic thing to remember which makes life really much simple in equilibrium statistical mechanics. Now, equilibrium statistical mechanics is the discipline I explained at large yesterday, that we at length yesterday, that this is the one we use to describe phase transition and all these things. So, the say pressure of a system or energy, enthalpy, what we do in terms of the radial distribution function, the thermodynamic properties, and that a very important quantity is two particle correlation function, that will do probably somewhere 10th lecture from now will come the radial distribution function, which is the quantity which is observed experimentally in a many different ways. So, at one side of this equilibrium statistical mechanics is this thermodynamic properties like entropy. Other side the is the information about microscopic arrangement, how molecules are arranged around each other, and as you can understand, this microscopic arrangement plays a very important role in chemical reaction. If two reactants A and B are going to react in a solvent, which is the common scenario that we do, then that is done through through the certain equation of motion, but the intermolecular arrangement plays a very important role. All this information comes out of equilibrium statistical mechanics, and equilibrium statistical mechanics is a very major discipline, not taught here, but in when I was doing PhD abroad, then we had 3 courses in chemistry department on equilibrium stat mech, and going over to time dependent in the last semester, last 201, 202, 203. From 20 the graduate level course used to start. So, physics also had 3 courses. So, this was the kind of importance given to that, and everybody was made to take 201. So, then quantum used to start at that level, somewhere like 2006, 6 or 7, quantum used to start. However, in between there is a difficulty, but now again StatMech is becoming very popular because we are having all these computer packages, and we can calculate many things. Another thing that is of much interest these days is the nanomaterial synthesis and the nucleation phenomena and the phase transformation, which is connected to phase transition. That is also comes under the essentially view of or at the borderline between equilibrium and non-equilibrium statistical mechanics. So, this is the preamble I will probably give in every class, that why we need to study and what is the basic perception, but every day it will be different. Different things I will bring in to motivate you and keep you focused into this subject, which is I think a formidable theoretical discipline. We do a lot on quantum mechanics in chemistry particularly, but the advantage of quantum is that by the time you do quantum 1 or by the time you do certainly quantum 2, you are into Ruthan's equation and all the perturbation theories are done, and you go to numerics. So, it is fairly easy from there, and there are all the packages which are amazing packages. So, huge number of people doing quantum, and it is easy to publish papers because of the interface with organic chemistry or materials, and they deal with molecules, and chemists love molecules. In statistical mechanics, we also deal with molecules, but rather with molecules is taken in terms of intermolecular interaction and also molecular shape and size. So, there is always good to keep these two in mind. Now, coming back, so what we did yesterday was that I said the most important relation in the entire statistical mechanics is this relation. And as I said that this was derived in as a function which gives a measure of the state of the system by Boltzmann. However, this it was brought in equilibrium statistical mechanics, used in its present form by Willard Gibbs, J.W. Gibbs, and there is really no derivation of this expression as such. So, this is to be taken as a definition. That is a very important point to remember. This important thing from which whole of equilibrium statistical mechanics follows in its entirety is because of this Boltzmann formula. So that is why in his grave and also in his bust in University of Vienna where he was, they have just written this formula. In his also graveyard, just this thing is written. You can do a Google, you can see them. I saw the bust in Vienna, and of course they are, that is the University of Vienna those days because of Austro-Grecian Empire, no? Austro-Hungarian, good, Austro-Hungarian Empire, the Vienna was the capital, right. So it was great people were always, including Mozart and many people were in Vienna. It's much less crowded now. Actual population of Vienna is now less than what it was, I think 50 years ago or 100 years ago. Okay. So how do we go from here and start? So I would prefer to consider this, that we have two postulates connected by an ergodic hypothesis that we start the statistical mechanics, but two postulates connected by hypothesis is great to say that we really have ensembles and everything come in, which is so much in the fast microcanonical ensemble. But these also should be regarded actually more of a postulate, except that one can show, unlike the two postulates where you do not, you cannot prove them a priori, you prove them posteriorly. That means similarly thing here also no a priori motivation, or probably there is motivation, there is no a priori proof or A of that. What is subsequently shown is that this function is the same function that we call entropy in thermodynamics. And entropy in thermodynamics, you remember, is given by the Clausius and it is dq reversible by T, right. So that is the way the connection between thermodynamics and statistical mechanics, which is very important, comes. So I will go, and then I think one of you had a question, so please ask the question. So now the basic idea then was that we start with to consider a small variation in microcanonical ensemble. This is a system is characterized by total number of particles, volume V and energy, which are fixed. But I can always consider that I can change the number by little or volume by little, or I can change the number energy by little. So that's, then as a result of these variations that I do, there is nothing wrong in this and nothing obscure about this, okay. So I get the variation of entropy as ds. However, this already beginning to tell you something very interesting, that because you have seen these kind of things, ds dv, ds d, because this is we routinely use it as a temperature in our derivation, but even aside from that, you have this Euler's equation, Euler's relation. Euler was a mathematician who started doing his study at the age of 24, and for mathematics 24 is really quite old. And then he did some amount, that means for few years, not very long time, but he has done huge amount of work in a relatively short period. I think he died young also, but he is in every field. You go to hydrodynamics, there is a lot of contribution from Euler. So essentially to Euler, there were certain combinations, and a very interesting combination, that temperature is the conjugate of entropy, or entropy is the conjugate of temperature, pressure is the conjugate of volume, right, and the chemical potential is conjugate of number. You know it in many different forms. If I call it free energy G, then I will bring it on this side E minus Ts. E minus Ts is E plus PV, E plus PV is the enthalpy, and then enthalpy minus Ts is the free energy. These things go over both in the G and A, where Helmholtz gives free energy, but it is the same. However, this one now can be used with certain variation, because we know it dd equal to TdS minus PdV. That condition we have in these are the relations that follow from these things. Why you are doing that? Why we are doing Euler equation and all these things? Because we want to get a handle on these things. And that then gives us the one that I want, ds dv. From this relation I get ds dv equal to p by t. And you have to understand, just like in the Newton's equation or Schrodinger equation, we write down things, okay. They are a very strong plausibility argument. We write them down, as you know very well, there is no derivation of Schrodinger equation. It was written down by transformation. So here also one writes down things and then see that whether they work or not, like this most important equation. Okay, then this is of course we know very well, this is for multi-component, not necessary for multi-component, but this is the your familiar equation. So now you can call that, you know it very well, that this is then indeed is the entropy. The advantage of that now, if I make this identification, the advantage now is the following. I can know from microcanonical ensemble, these are the conditions. That means temperature is the derivative of log omega with respect to energy, which intuitively makes sense because omega is the total number of microscopic states of a system belong to a system in the microcanonical ensemble characterized by NVE. Then if I change a little energy, then the number of microscopic states that increases by this quantity 1 over T. Okay. Now, similarly you can have definition of pressure in terms of microcanonical ensemble, then you can have chemical potential in terms of d omega v. Now, this has a very interesting one corollary which I will discuss a little later if I come. So, this is what the thing that I wanted to review of the microcanonical ensemble. Then you may continue to do canonical ensemble. Now, you have, one of you had a question, yeah, please tell me, in microcanonical, in MD.
So they take, means they use this ensemble, but in the phase transition type of but when phase transition actually there is a the effect of pressure.
Right, very good question. Yeah, excellent question. So, when you do these calculations, these like phase transitions, and this creates an enormous problem, and I give you a problem. We do NPT. Like I give you an example. Right now, we are doing, and also do we Gibbs ensemble. That means because number of particles exchanged, and that is mu pt. That means that's the Gibbs ensemble. NPT is isothermal isobaric. So, all these things all these different ensembles are brought in, but at certain cost, and I tell you the cost. Right now we have been trying very hard to study ice water interface. Other people have studied, you can see several papers are there. So, two things we are trying to do. One of them is that the why, it's a very interesting question, we are just writing the paper, that if you take like argon, which are characterized by Lennard-Jones potential, then the FCC lattice and the liquid interface is rather broad. It is about 4 to 6 monolayers or molecular layers, but water interface is sharp. So, we try to understand why water interface is sharp, and it is a huge importance, ice water interface in many different contexts. And we came to that. From there is a class of proteins called antifreeze protein, which is a lot of threonine with hydrogen bonding, So, these antifreeze proteins with a large number of threonine, they stop ice growth or ice remains static. So, we want not just to growth, we also, so from there we went, okay, let us just study the interface first. And I knew this problem because it is a very difficult problem, because when the something an interface is 4 to 6 or 8 mono layers, then you cannot study them by any experimental techniques, you know. Like I cannot do neutron scattering on that needs micrometer or millimeter length. I can do imaging, but the spectroscopic imaging cannot study that length scale. I can do TEM, but TEM means it's static, it is not dynamic. I wanted to do the fluctuations at the interface. And then when we try to, my student is trying to, two students are trying to stabilize NPT, it is a hell of a problem, because they just either the ice melts back or the ice forms. That because there is a barostat, an idiotic barostat is giving forces into the system, and then of course there is a thermostat. So the people who are continuously studying in NPT or Gibbs ensemble, they have this difficulty, and you are right, there is no way I can do NVE in that system, because if I do NVE, then I will not be able to remove the latent heat. Say latent heat has to be removed, you know, otherwise I can stabilize and remove everything and say it is NVE, then that will stay in that system. Unless I can have such a large system, an humongous system, then NVE will be able to capture, because this growth of crystal or melting will be captured as a fluctuations in the system. But that is not possible here. So, but the kind of systems we do, we have maybe 5,000 water molecules, and people are doing, those who have done successful simulation, they have a very long, they have a crystal slab and then liquid on the two sides, and different people ask different questions. So, you are absolutely right that there is this huge problem, and that is why there are two kinds of simulation people. One are the people like us who are application and not respected, and there are people who are developers who develop potential, develop methods, like these guys in Italy, what is his name, Perinello, those who then Torian value, who did umbrella sampling. Perinello group did many things, ab initio plus metadynamics. So, the way to come around these things in phase transition, then use this specific sampling, you know, that means you, which are called method of constraints, which are like our Lagrangian multiplier, which are method of constraint. You move things around in the direction you want it to go, and you equilibrate along that. That is the way you do the simulation. So, there is a huge problem. One probably should, I have 2 chapters at the end of my book on computer simulation. I want certainly to do the chapter 31, which is on computer simulations, where I have devised new ways of doing periodic images, minimum image convention. I did in terms of Ising model, and it's so easy to see what is the method of images, the minimum image convention, periodic boundary conditions, but that is in the chapter 31 of my book. It is very simple. I was not happy with the conventions, the explanation given in Allen and Tildesley or other books, because it seems too complicated. It is so simple a method, but then you take the one dimensional Ising model, all these explanations and all these statistical mechanics becomes much simpler. Okay. So, does that explain partly your question? It's a difficult question, and difficult to answer at the same time, because that is not done. Okay, now, so we now from then on we went. So what will happen? I'll be spending more time on this, because I want you to be comfortable, because this is intimately connected with all our simulations and all the interpretation of our results, that how we do statistical mechanics. And once we become familiar with this, is really very, very, very nice things. And you can, you see, when you, for example, you are doing lattice calculations, very recently all the surfactant work, all the lipid bilayer work were done by saying how many ways I can pack things, and then how many ways you pack things, from there you get omega, and then you go on from there. So, this is the partition function. So, in microcanonical ensemble, omega is the partition function, or sometimes it is also called, so in microcanonical ensemble, this is the partition function and this is the thermodynamic potential. Thermodynamic potential is the quantity that takes an extremum value. Actually, if you think of that, you always maximize the thermodynamic potential. So, free energy we write as kBT, but the way it should write as a minus kBT. So, that is the one that follows from Boltzmann's arrow of time, which was Stephen Hawking and all these people wrote so much book on that the arrow of time is because the entropy, a system left by itself goes to a state which has maximum entropy. That is the Boltzmann's principle. And okay, so then from, but as we know, microcanonical ensemble, please ask questions. Microcanonical ensemble is not very useful. So there are several issues. One issue is system at equilibrium but away from phase transition. The properties of water, properties of acetonitrile or dimethyl sulfoxide, or properties of a block of iron or whatever solid. There is one thing like that. Another thing is phase transition and the many other aspects that we study. So, when a system is at equilibrium in a stable state away from phase transition, then if we have to describe that, then NVE is not the greatest of the system, because we are too much constraint. Real world NVE is not there. So, we have to go to now we start relaxing. We go to NVT, then we go to NPT, one by one we will do that.